Well, howdy, physics sleuths and inquisitive souls, and welcome again to another episode of Dynamic Gravity. So, this episode, or lecture, we are going to do some really big things. I'm going to calculate from my math that I've created what is the size of the universe currently. And we are going to go into a little synopsis of how the universe ends, or whether it's infinite. Spoiler, it's not infinite. And yeah, then we're going to go into a few other things too about the cosmological landscape of our great, vast universe. Uh, as I see it, as the world's foremost leading authority on dynamic gravity, which hence makes me the world's foremost leading authority on gravity, period. Because, in case you haven't quite get it, this, if you're new to my channel, it's your first video, I am the only human to ever live who can perfectly calculate gravity, dark matter, and dark energy with the same formula and explain everything. Everything. You want to keep believing in GR, an inferior theory which cannot do hardly anything that dynamic gravity can do? Be my guest. It's a free world. Do whatever you want. But know this, I am, irregardless of how you think about me, the world's foremost leading expert on gravity. It is what it is. And I can already see it now. Every episode, there's always someone complaining about my cough. Yes, I have brain damage. After 9/11, when the Twin Towers got taken down, I immediately went and signed up for the Army to serve my country against the big bad terrorists who want to kill us all. And in doing so, through acts that were no fault of my own, I got blown up and I almost died. And now, against all odds, I survive, but not without a cost. And that cost is brain damage that manifests itself in what is called an epileptic tic. I'm sorry if it annoys you. Imagine how I must feel having to live with it to the day I die. It sucks. But this is the way. So let's swim forward towards our goal. But, as always, we're going to need a little motivation. And I think I know just the man to give it to us. White Shark. That's the right man. He's going to swim just behind you, making sure you keep your pace. Oh, you better not be slacking on your pace with White Shark, man. Or he is most definitely going to get you. Oh, White Shark is going to get you, man. White Shark is going to get you if you slack off. He's so hungry. He's going to take a bite. So, let us begin then. Alrighty. As with all things, it usually begins with whatever the current accepted theory is, and we'll start from there. So, let us go to my favorite source, even though they hate me, Wikipedia. That's right. So, in Wikipedia, we got to learn the concept of redshift if we're going to talk about the cosmology and the size of the universe. Because the redshift is basically the distortion of the spectrum that we measure of starlight, galaxies, whatever, this stat. And in doing so, and how much distort it in various ways, my current belief is that we can kind of get some sort of an idea of how fast things are going. And this is true to a degree, but it's complicated. It's definitely complicated. Transferring redshift into velocities, recession velocities of galaxies, and the expansion of the universe. We're gonna dig into this. This is gonna be a deep, long episode. So I know you guys love it when I do these hour and a half long spiels, but it is what it is, man. If you go to a freaking college and you take a physics class and the teacher is teaching you the concepts of momentum or whatever, is he going to do it in 5 minutes or is he going to take an hour long lecture? Some things just can't be rushed, and I'm so sorry. All right, wave shift or red shift, increase in the wavelength corresponding to decreased frequency of photon energy, electromagnetic radiation, blah, 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 blah. So we got our spectrum and it gets shifted. That's what it's basically saying. History, blah, blah, blah. We don't care, blah, blah, blah. Not interested. Excuse me. Here is the basic calculations for redshift. And it's just basically saying that Z, which is the redshift, is equivalent to the emitted frequency change divided by the emitted frequency. We're going to dig into this in a little bit and eviscerate it, as we always do with all things, because that's how we roll on this channel, man. We're crazy. And if you notice, there's all these different formulas to calculate redshift because none of them are right. And so they're always trying to hybridize, bastardize, modify the formula to try and make it not spit out garbage. But they don't even know if any of these are really accurate, to be honest with you. You know? This one I think is more for maybe relativistic speeds. This -1 helps keep it a little bit lower. We'll go into this. We'll go into it all. Here's the more formulas. Redshift, relativistic Doppler using Minkowski space. This is kind of like a Einsteinian sort of formula, but this is for low speeds too. This isn't even, as you can see, this is only when the speed is very small. Okay, it's not even close to the speed of light is when this works. As far as I can tell, none of them seem to work when the speed gets closer or approaching the speed of light. And I got a new math formula that I created. I was blazed out of my mind, high as a kite, and as I usually am when I'm thinking about these things. And you know, God just sent another image into my brain, and I couldn't ignore it. And so here I am on this big long track in this rabbit hole, trying to figure all this stuff out. As I should. Who better? To be perfectly honest. Let's be honest. Who better? If not me, then who will do it? Here's the cosmological redshift. All right, this I believe is involving like Hubble's law. I think that's Hubble's number right there. It's the distance of how far the galaxy is, and times them together, and you can kind of get the velocity. Of course, here they're divided by c to get redshift, but you can get velocity out of this. That deals primarily with space-time, though. With the universe expanding, space-time expanding for no reason, because they don't know, because general relativity is a clown shit show. And so they have to make up these things to justify the observations they see when they look up in the sky at night. And this is one of those bastardized hot fixes. Patches to theory of general relativity to keep it going. The resurrected is a zombie theory, even though it's failed miserably, almost all accounts, aside from time dilation, which my theory has too. So, really, general relativity is just complete garbage, aside from time dilation calculations and their math of that, which they use tensors, and that's not even space-time. That's just a coordinate system that is being used to calculate geodesics as you travel through gravitational fields. It has nothing to do with space-time. But that's how they interpret the math because they have nothing else. They don't know. They don't know. They have to have something to say. So they made the space-time. That's what it is. It's not real. No experiment has ever seen or confirmed or even get a glimpse of space-time ever, ever. We got gravitational redshift here, okay? Now, my theory also has this as well. The gravitational redshift. We're going to go into this. This is basically, these are the three types of redshift that they say they currently think exist. You know, the regular one from speed moving, the one from the expansion of the universe, space-time, and then this one from gravity itself being able to affect a photon, or at very least photonic generation, as it's being created. And so that will drag the photon out as it's being created, giving it a redshift. So if like a black hole, I know black holes really don't emit photons, but let's say something like a very, very powerful star, does, um, it would be expected to have a gravitational redshift from that. And we actually do see this. Here is a paper, gravitational redshift. This team thinks they've confirmed, isolated, and measured the gravitational redshift from photons coming from the sun. And according to Einstein's theory, or his math anyways, it's a very small redshift, like 1 part in a million gets shifted over. It's very, very minute, but we have very good, electronics, so we can measure this. The team says, however, it was difficult because plasma is constantly moving from the sun. As you measure those, are going to have a velocital speed to them that's going to also give you, a blue shift or red shift, depending on which direction it's going. And this is causing all sorts of havoc. But eventually, they believe they are able to get it. And I believe, yeah. Measurement error is excellently in line with the predicted value. So this is what is, according to Einstein's math, what should happen is 6.33.1 to s to the minus 1. I think they're able to measure 6. Oh my God, you can't see it. I'm sorry, I suck. Yeah, so here it is. 6.33 is what is predicted, and what they measured is 6.38. So it's pretty close. They believe they're definitely measuring a redshift from gravitational fields, and I believe them. My theory also predicts this, not just general relativity. My theory also predicts time dilation and hence gravitational redshift. They're basically the same thing, from the same thing. And if you want to know how that is, what's going on there, let's see. Here is our last lecture on my experiment, the magnetic field. Okay, so the way my theory predicts time dilation and redshift essentially is you have an atom. Okay, let's keep it simple. Let's say you've got a hydrogen atom, and so this is your proton, which is your down quark, and then your 2 up quarks, which are really just 3 up quarks surrounding, fighting for control of an electron. Essentially all it is. They won't tell you that, but that's what it is. And then you got your electron right here. Boop, 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 bop, 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 bop. That's in orbit around. Okay. So make this electron a little darker. All right. So what happens is normally any sort of chemistry that takes place is going to involve these electrons shifting and moving around, bonding to other atoms to create molecules. Or if you're going to create photons, this is going to move slightly from photonic energy that hits it, and it's going to re-release that from the right-hand rule, as we've learned in our lecture on deep diving photons. It's going to create photons spitting out beep, 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 like that, right? But let's do a thought experiment. Let's say we are in an immense gravitational field, okay? Now, according to my theory, an immense gravitational field is essentially the displacement of the proton's electromagnetic force being displaced outward infinitely through whatever. And let's say that you have enough protons shoved together that this displacement is out, and you have this huge gravitational field. And this huge gravitational field is essentially the positive field of a proton. So it's absolutely going to affect the electron. Whoa, 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 whoa! Why are you? Oh my gosh, I don't even know what the heck is going on here. Okay, so as you're in an immense field that is going to be emitted, right, from a gravitational object, this huge displacement. Let's say this field is coming, these are all virtual photons, right? Potons, whatever we want to call them. As they're coming, they're going to be interacting with this, right? And the stronger the field, the more of these they're going to be coming to interact with this. Well, as they interact with this electron is going to be sucked up interacting with these. So that is going to slow down its ability to perform chemistry. Chemistry meaning moving in any way to form a bond with molecules and creating photons. So the stronger the gravitational field, the more it's going to be affected by this, and the less it's going to be able to generate photons, interact with photons, and to create chemical bonds, covalent bonds, and sort of like this, and any sort of chemistry. So basically, what time dilation is, it's not actually time. You're not affecting time at all. Time remains the same pace that it is everywhere. It does not change. But you have the effect of time dilation, which is where anything that we use to measure time, such as, say, an atomic clock is going to be bombarded with photons, and it's going to be radiating these photons at a specific frequency. And this frequency we measure and calculate, and it turns out to be one of the most accurate clocks the world's ever known, like cesium clocks or whatever. But the stronger the gravitational field, the less available this electron is to perform these actions, and the slower it is going to be at doing that. So, although the rate of time does not change, any tool we use to measure time is ultimately based upon some sort of chemical interaction of the electron and proton, whether that be chemistry, and if there's no chemistry, then you have an object that's essentially frozen in time and does not age, time dilation. Or, like I said, photonic generation, creating photons, it's going to slow it down, which is going to give it a redshift because it's going to draw out the photon. So that's basically how my theory says that time dilation and gravitational redshift is going to happen. What's going on there at a subatomic level. Notice how general relativity can't give you the answers as to what time dilation is. All they can do is just give you some stupid, mathematical trick, like a chart or some bullshit, and say, and this is time,
and this is space. And as you go up in space, you go up in time.
Okay, what? You didn't answer anything. All you did is give me a bullshit answer. I mean, I could literally say something, is obscene as like, it's the same logic as,
This is a graph. And as you can see, the more you fuck around, the more you find out. Find out. See? The more you fuck around, the more you find out.
same logic. What are we doing here, dude? And this is the state of physics, modern physics, okay? And they think this is an adequate answer to explain time dilation. It's bullshit. They don't know what they're talking about. So, just to let you know, yet another failure of general relativity. Although it predicts time dilation, it cannot tell you what it actually is or how it's happening. They can't do it. All they can do is give you math tricks and graphs that are coordinated and blah, 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 blah. Don't mean anything. Nothing at all. So, that is an explanation, time dilation, and gravitational redshift, according to dynamic gravity, anyways, just so you know. Now, as we go back here, you can see, look, z is equal to velocity divided by c. C is speed of light. Velocity is how fast your object, your galaxy, is going away. So theoretically, if you divide how fast it should be going by the speed of light, you should get the redshift, and you can move this formula around to get velocity from redshift just by timesing it by the speed of light. The problem is, it only works if the velocities are very small. And by small, I mean about, do they have a graph here? I'm sure they have the graph. They have the graph. I know they do. So yeah, redshift going away, blue shift coming to you, blah, blah, blah. More formulas, trying to make it work. Cosmological redshift, blah, blah, blah. Gravitational redshift, blah, blah, blah. Look at that. That's all Minkowski's right there. 2gm over RC squared. That's how he does his math. Okay, observation and astronomy. Okay, now if we look, here it is, right here. This is their math in action. This is what is it? Yeah, distance, and this is the time. Well, isn't it? Convolving distance, gigalight years. You know what? I'm not even sure if that is it. Cosmological distance, look back with a Planck. Okay, maybe that is different. Okay, don't worry, I got this somewhere else. Here is a paper that was released deriving accurate peculiar velocities even at high redshift. So this guy is like, yeah, dude, the math is all straight up. I'm going to try to fix it with my, blah, 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 blah. And he's like, yeah, here's a formula. Here's the Hubble constant, distance, da, 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 da. That would be the cosmological redshift. Here is him using different math tricks. Even when velocities are non-realistic, blah, blah, blah. I think this is what he started out with, and I think he tried to bastardize this formula to make it work better. Now, here's a graph of velocity according to the formula versus velocity according to Hubble constant, okay? See, they're pretty much in line, but we are only at 1/10 the speed of light. So after 1/10 the speed of light, the two formulas, one from the Hubble and one from physics, diverge greatly. How much do they diverge? Quite a bit. I believe this is that it? Redshift. Yeah. See, like here you can see like redshift after approximation. I believe this is him trying to fix it. And I think he's bragging about what a good job he did. And he did. He did, improve it. But that doesn't mean his math is right. It just means that it goes in the right direction, and the two are not the same. They're totally different things. Um, but yeah, so inferred peculiar velocity. So yeah. Here we go. Here's what the formula. Here we go from Hubble constant says it should be. But as you can see, at about 1/10 the speed of light, the actual velocity starts going off rapidly. And so by the time you're like at, half the speed of light or, 80% the speed of light, the two are so divergent that you're not even in the same universe. You're literally almost one universe over. That's how bad the math is.
Relativity.
But you can just see, all the efforts that people use to try and, make sense of the redshift. Because it is a useful tool if you understand it. But the math that they use just doesn't work out. It just doesn't. So, redshift, blah, blah, blah. So, let's take a look at exactly how we calculate this redshift so you know exactly what we're doing here, what we're going to be doing to it, okay? Measuring redshift. To obtain spectrum, we'll say galaxy shows spectral lines from blah, 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 corresponds. Okay, now, hydrogen is probably the most used element when they're determining redshift because it's the most abundant. Everything has hydrogen in it one way or another. The other things, not so much. And they have a pretty good study. Here are the wavelengths of hydrogen measured in a laboratory, right? Here's all the peaks, as you can see. And here is a chart of an actual galaxy. This is a real chart that was taken from a galaxy. And you can see this right here is one of the hydrogen lines that they're talking about at 72 out. But as you can see, this is the alpha line. It should be at 6,500. So it's redshifted by like 700 or something. So yeah, here's what they calculated, okay? Yeah, 7,200, but it should have been 6,500. So it's redshifted, it's stretched out. And they can measure this, by simply knowing the wavelength from the bottom and seeing how far it goes over. Like, oh, boop, 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 there it is. Oh, there it is. So, yep, and it should be there. So, nope, dot, dot, dot. Simple. And then what they do is, of course, now use the math, where you basically take the z observed and divide it by the rest. Or, right here, so 4,700 divided by 4,300. And then you minus 1 because they're trying to keep it under 1, so it's not faster than the speed of light. And you get 0.1, which means theoretically this galaxy right here is going 10% the speed of light, is how fast this redshift is saying it is. But it's a little more complicated than that. And as they say, it's really a lot harder to just simply plug in and do the results because the formulas spit out garbage. You do that. So they have to have all these fixes and different forms of things that cause redshift. Like, oh, in space-time, obviously it must be causing a redshift. Otherwise, general relativity is broken. And that can't possibly be the case. So space-time is causing redshift, but it's not. They teased me with the actual advanced formula for relativistic speeds, but they never give it to me. Always with the tease. So yeah, so of course I tried to take their resources here because they have all different charts. And it looks like you can't see them, but when I click on them, it brings me actual galaxies that are measured with their actual redshift. The problem is, though, I don't see any identifier for what galaxy they're measuring. I don't know what kind of clown would show this level of data about galaxies, but then hide the identity of the galaxy itself, keep it anonymous. Like, well, I want to know what galaxy it is so I can look up and find out, how far it's estimated to be, how large it is, blah, 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 what direction it's going, all these things. But unfortunately, I couldn't do that because they don't give me the proper information. And this is a problem. I tried to look to find a catalog of spectra of galaxies. I could not do it. Once again, if you're not in academia, you don't have access to a lot of these resources, and it's really hard to formulate theories. It's just another way they try and gatekeep anyone that's not them out of the field. But I am what I am, and I was destined to be the man who conquered gravity. Gatekeeping damned. They ain't gonna stop me. Destiny is a little bit higher source than that. So, what I've been resort to doing is looking at this website, which actually I found pretty good. They have a good little, video synopsis of like, hey, this is what a redshift is, da 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 da. And it's pretty nice. They got a lot of stuff going on here.
You have
Let's see, here we go. There's full spectrum, emission spectrum, and absorption spectrum. And of course, you're usually going to be dealing with probably emission spectrums, but if it's covered gas, maybe absorption spectrums. It could be either. Depends. Here we got the equation once again, where for Z, we have observed minus rest, which is change in wavelength, divided by the measured wavelength in a laboratory to get the ratio that you would then simply times by the speed of light to get speed. But like I say, it doesn't work, but I'm going to make it work very soon. Very soon. Give it a couple more minutes. So this I came across, and this is just basically generic writing according to Hubble's constant expansion. Remember, I showed you the formula where you just times Hubble times the distance, and you get the velocity. Well, they are rearranging that formula slightly, and what they're doing is they are taking how far away the galaxy is, the distance, and times it by Hubble to get the distance now. Or no, my bad. What is this? No. This is something totally different. My bad. This is if if it were traveling. They believe they have this general rule of like 20%. So if you measure a galaxy to be like, I don't know, 10 billion light years away, then it should be actually 20% further away. But in actuality, the way this works, damn it, how does I had this all figured out last night? Of course, I've screwed it up. Well, anyways, yeah, they're timesing this number, like how far away it is. And the further away it is, the bigger the number gets. So it's kind of like an exponential curve going up, right? So you got these galaxies, right, that are 13 billion light years away. And these would be among the furthest galaxies away. This would be if it had a redshift of 10. Right now I think the highest redshift they believe exists is like 14, 13, whatever. So that would tell you then that it doesn't go up much more than this. It probably wouldn't be but 14 billion light years away, not even that, probably like 13.5 billion light years away. But as far as this, it would be probably like 30 something, 31, 32 billion light years away because of the time that the object has been traveling at that speed, coming in from Kobe did from when it was first emitted. All right. So this is basically kind of the expansion of the universe. This is useful to know. So this is basically telling us that, listen, if there's an object that's 13 billion light years away, it's going to be double that, okay? Double far away in real time, if it still exists. We're going to go into that. Okay, let's move on. Here's another formula. I know they have all different ones, just to show you how bullshit the redshift is. It's almost an arbitrary number at this point, because look at how many different ways they calculate it trying to make it work, and they can't make it work. At any time they measure a high redshift object, it's going faster than the speed of light, which is impossible to Einstein's theory of general relativity. It's not impossible to my theory, but there has to be very extraneous circumstances to allow that. It has to be shielded from all gravitational effects to be able to do that. And that's just not going to happen with the galaxy. It's just not going to happen. So according to my theory, you could basically say that a galaxy should never be able to travel faster than the speed of light. If it does, we're going to go into this. But I just want to show you, there's even more, BS and stuff as far as them trying to make this number work, okay? So, now we're going to Hubble's law. Here's what I said, Hubble's law times the distance equals velocity. But, as you can see, it's all over the place, man. It's so far divergent, it's not even funny. Okay, and they have all these different rearrangements trying to squeeze the most out of this to make it work however they can, but at the end of the day it doesn't work. I'm sorry, it doesn't work. You can't make it work. All right. Now, so which galaxy do we know that's moving the fastest away? Okay, this seems to be probably the best answer I've gotten, even though it's from a forum. It's not an actual legitimate website, but sometimes you get really good answers here, and it's just the way it is. This guy says that the fastest galaxy he knows is G-Z11, and this does not have a date. Yeah, it looks like 2019, and it probably was back in 2019 before the space web was launched. And it had a redshift of 11.9. Okay, remember the highest redshift we have now is like 14, so it's gotten even more crazy, way more crazy. Now, using Hubble's law and calculating the velocity, which is the most accurate way they have to do it at such high redshifts, which is why they do it, they get an answer of 670,000 kilometers per second. The speed of light is 300,000 kilometers per second. So this galaxy, which is like 5 years old and outdated and not even close to the fastest galaxy now, is going at more than double the speed of light. And he says, well, the reason for this, though, is not that the galaxy is actually going faster than the speed of light, because Einstein prohibits that. But what's actually going on, the velocities of the galaxies are actually much lower, only a few hundred kilometers per second, like, only maybe 10% of the speed of light. But the recession of space, which is, the Hubble says that space-time is expanding, hence the Hubble constant. And so that is what is attributing to like 90% of this redshift. So he claims. And so, academia claims. So general relativity lovers claim. Because as you can see, if you don't have some exotic measure to fix the math just goes absolutely bonkers. And it goes insane. So, just to let you know, that's what's going on with that. Now, according to Einstein, he says that you cannot go faster than the speed of light. Because magic. I don't know. A fairy farted and pixie dust came out, and the pixie dust prevents you from going faster than the speed of light. This is Einstein, what he says. Prove me wrong. But I have a different reason. Okay? As I said, it is possible to go faster than the speed of light under certain criteria, but a galaxy is not going to meet those criteria. Definitely not. So, what's going to happen if a galaxy travels faster than the speed of light is galaxies are made up of atoms, okay? Atoms like our hydrogen atom, which is, remember, one up quark, two down quarks, and an electron, okay? That is an atom. Now, if this atom, let's say, goes incredibly fast, like boop, it's got so much velocity, man, super velocity, it is going so fast. What's going to happen, according to my theory, is if it breaks the speed of light, or even if it approaches the speed of light, at a certain point, all chemistry is going to fail. Okay? Remember when I told you in this episode about time dilation and how time dilation, what causes the gravitational redshift, according to my theory? Well, this is not far from. Okay? So you have virtual photons, right? They're interacting boop, 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 with between this proton and this electron, okay? And they are interacting, they're exchanging information, they're exchanging force, they're keeping the distance, keeping the equilibrium, so we speak, so that everything is the lowest possible energy value as part of the law of conservation. Now, as your atom goes faster, like whoosh, faster than the speed of light, guess what? These virtual photons travel at the speed of light. Because essentially, as I have claimed in previous lectures, they are essentially virtual photons are extremely low energy photons or photons, depending on what is making them. Okay? So, it's basically a photon, is what a virtual photon is, but it's an extremely low level energy photon. And that is kind of the placeholder of what's going on. So as this whole atom is traveling faster, or as fast as the speed of light, the ability of the virtual photon to relay at the speed of light and convey with this electron to keep it in line, to keep it in line so it doesn't go off or get too close and touch or whatever, blah, 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 blah. It is not going to be able to keep up with the speed. So one of two things is going to happen. Either A, what's going to happen is this electron is going to fall behind as the atom is going in this direction, right? Boop, boop, boop. It's going to fall behind because these can't keep up. And they're going to try, but they're not going to be able to. And so they're going to be barely keeping up if it's at, near the speed of light. So essentially, all of the electrons are lagging behind the protons, and every single atom and every single molecule in the entire galaxy. This is going to severely inhibit chemical reactions beyond what the time dilation itself is doing, which is slowing them down to almost a grinding halt. So, on top of that, you're going to have this distortion effect of an atom which is going to completely destroy all chemistry. It will probably destroy all chemical bonds because there's no way you can have chemical bonds at the right angles to create molecules if every atom, the electrons are lagging behind of the proton. And if it actually goes faster than the speed of light, or perhaps the speed of light itself, then these virtual photons are going to be ineffective in doing their job of keeping this electron near to affect and stabilize the atom. And so essentially what's going to happen is the atom itself is going to disintegrate. And you're just going to have a bunch of electrons and protons. But that's not even the end of it, if only it were that. Because also, keep in mind, as I've said, according to dynamic gravity, the proton is actually 3 up quarks and 1 electron in the center. And they're fighting for control of this. Well, that also is exchanging with virtual photons, but the way they do it, they call it the strong nuclear force. Because the way that it manifests, when all the 3 are that close fighting for each other, that's how the forces kind of manifest. And they know this because they have unified all the forces. They know that electromagnetism is essentially the strong nuclear force at a certain level, as is the weak force. They've unified these forces. They are all one, just in different manifestations for different purposes. Okay? This is one of those purposes. So even the proton itself is going to disintegrate and to come apart. And so basically all you're going to have is just this soup of protons and electrons that are essentially going to be disintegrating themselves into their most elementary form because the virtual photons can't keep them together. So if a galaxy ever did truly reach the speed of light, based on what I'm trying to say to you is crazy weird things are going to happen, but at the end of the day, any life in that galaxy is dead. It's going to disintegrate. It's going to do a cellular degenerate. It's going to fall apart, and the time dilation can be so severe. It's essentially going to be trapped in time in any ways, and static. So this is what the boundary of the universe is. It are galaxies that are being pushed from the positive or anti-gravitational forces of gravity according to dynamic gravity, which you would call dark energy, that I calculate with my formula. Like it's just a regular part of gravity. Because my theory of gravity has a built-in anti-gravity component because it's all based around positive and negative charges that repel each other, and they're interacting in different ways. That's what's going on here, okay? So basically what I'm trying to say is the edge of the universe is going to be a bunch of galaxies that are in a very slow but steady state of disintegration that are just being withered away to nothing but elementary particles. Nothing can survive there. So the edge of the galaxy is essentially this barrier of speed from being pushed by all the supermassive black holes working together to push the outskirts of what remains in into the furthermost boundaries, okay? Now, this is only a fraction of it. It gets so much crazier. Okay. So, that's the edge of the universe. There's no real actual physical edge. It's just simply a barrier of galaxies that are just going too damn fast for their own good and they're being disintegrated in the process. So we want to know, where is this at? Well, first of all, let's prove beyond a shadow of doubt that the universe is not infinite. Okay? If the universe were infinite, according to my theory of gravity, you have supermassive black holes. They're interacting with each other. Their gravitational field is extending so far out, so strongly that it's interacting with these, even at extreme distances, like between us and Andromeda and much further. They are still interacting with each other very, very strongly. So it gets displaced out. The more galaxies you have, the closer together, the further this gravitational field gets displaced out. And as I shown to you earlier, if you have a strong enough gravitational field, you have so much time dilation that all chemistry is completely halted, and your molecules or atoms are essentially frozen in time. Okay? So, if the universe were infinite, because all the galaxies, we can measure them, are definitely close enough to interact with each other, so they're going to displace the field out further, so even slightly further slow. There is a gravitational field, I assure you, that covers the entire galaxy. And if the galaxy were infinite, then this gravitational field would hence also be infinite, meaning that we would be in such a severely displaced gravitational field that there would be no chemical reactions. And in fact, it would probably just disintegrate us as going faster than the speed of light does, because you would have such strong gravitational forces, it would just rip apart all atoms as it does in super celestials, what we call them with dynamic gravity. You call them black holes and neutron stars, where basically the object is so strong with gravity that it is ripping the electrons and the protons apart from each other and creating this proton soup, the most potent thing you can have for a gravitational field, which is why they're so ridiculously powerful. It's insane. So that's what's going on when it comes to large external gravitational fields. And because we exist and the chemistry actions happen, we can be 100% confident that the universe is not infinite. Okay? It's definitely not infinite. 100% not infinite. Or nothing would be able to survive the immense gravitational field of displacement that would be created from infinity. It would be way, way uncomprehendable. Because remember, even a tiny fraction of infinity is still infinity. That's the whole point of infinity. It's infinite, which is why it's just a mathematical concept. There is no infinity in real life. It does not exist. And if you get an infinity, then there's something wrong with your theory or math. This is one of the problems of general relativity. They get infinities when it comes to like black holes. And so they say, well, clearly we know this is bullshit, because it can't have infinity in a black hole. It's got a certain amount of space it can have. But once again, it's the state of modern physics, and they don't care what I have to say about it. They really don't. So, let us continue, shall we? Okay, Hubble constant. Okay, now we're going to go into my math that I created to calculate redshift. Okay? And basically, what you need to understand is that redshift is a ratio. This number is ultimately just a ratio that's going to be used. Can I find it? Probably can't. I never can when I need to. Yeah, right here. So if you were to simply just times z times c, you should get your accurate velocity because z is a ratio. It's a unitless number that you are applying to your baseline, your base, which is the speed of light, to give you where it should be calculated. It's a ratio. And the way that ratios work is you have, 3 divided by the entirety, which is 10. Okay? So, excuse me, I'm so sorry. What we have here, this is the way they do it. They have change in wavelength, that's supposed to mean wavelength, divided by the measured wavelength, and that equals z. Ultimately, that's the way it's supposed to be, okay? So, what this ultimately is your wavelength observed minus from your wavelength measured divided by wavelength measured. Okay? This is the current formula for z. Ultimately, it's the most simplistic Ferrel state. Okay? But as you can see, when we start measuring redshifts that are shifted so far that they are shifted further than the actual distance of the wavelength itself, right here. Now you get a paradox. Now you get a ratio that's going to give you a speed faster than the speed of light. But this is impossible according to both Einstein's theory and my theory of gravity. It cannot go faster than the speed of light, except under certain special circumstances. Maybe I'll make an episode on that one day. Maybe. So many. I got a bunch of episodes to make. It is what it is. I'm a busy man. Okay. So, what I say is I have created, and I was high on my mind, and I made this formula, and it's almost identical. It's almost identical. Okay. What I say we do is we do the wavelength observed minus your wavelength measured, okay, to get your change in wavelength, okay? But the difference is, on my denominator, what I am dividing by is going to be the wavelength observed plus your wavelength measured. Okay? So, to give you the difference, this one is going to give you a ratio that is based solely upon the wavelength in its purest altruistic form, where mine gives you a wavelength or a measurement that is based on the wavelength at its ultimate measured form, which is what you're going by. And the difference might seem subtle. You might be like, what? Okay, let's do an example. Okay. So let's say you have a redshift of 5. Okay. we're going to do their formula, okay? We have a change, a wavelength of 5, a redshift of 5, or my bad, not redshift of 5. A change in a wavelength of 5. We're keeping it simple, okay? Just so we can do the math simple, okay? And the actual measure, okay, hold on, my bad. We'll do the actual wavelength, what it should be at is 5, okay? But we have measured a wavelength of 25. We've measured a distortion. It's 25 angstroms of wavelength over from the wavelength where it should be at, say, 5. Okay? So what that gives us is a Z of 5, a redshift of 5. Okay? That's according to their math. So they're saying that if it's 5 times greater than the wavelength itself, then theoretically you should be going 5 times the speed of light. But of course we know this is impossible. But this is the kind of stuff we measure all the freaking time. All the time when we measure the redshifts of galaxies. But if we use my way, what we got is, let's say, a change of 25, okay, divide it by 5 plus 25, which equals 25 over 30, which is now still a ratio. It's going to keep you out. It's going to keep you out, what's that? 5 over 6, which, I'm going to do the math right here, which is equal to 0.83. 3, blah, blah, blah. So, according to my math that I just made up, and I'm not saying that my math is correct, okay? In fact, there's a very good chance my math is not correct. But we're going to go into this in a second. My math is guaranteed to be no more than 10% off on any situation, and mostly off at the lower velocities. And the higher velocities, it's going to get more and more accurate. Keep that in mind. So, if we have a redshift of 5, my formula says it will be going about 80% the speed of light, which is fast, but not incomprehensibly or impossibly fast. Where the current mathematics they use say, no, you're going 5 times the speed of light, which is impossible. So that's the difference. That's the math that we're going to be using. And now you might be like, well, but how do we know this does anything? I don't know what this means. We're going to get there. Right now, I'm going to show you. Sup. Okay. I have to bring up my calculator. Okay. Good old Windows calculator. Okay. So we are now going to use my mathematical formula to calculate the size of the universe as it is currently from the observations that we are getting. Okay? Now, let's keep it simple, okay? Let's say the expected wavelength that is observed should be 1 unit, 1 angstrom, 1. We're keeping this simple so that our mind can comprehend how this changes over time. Okay? So, according to the formula, let's say we have a change of 1, and it is going to be divided by 1 plus 1, the change plus the wavelength, so you're going to be 2. You're going to get half the speed of light, okay? So if we are half of the wavelength, we are essentially, if we are exactly 1 wavelength, my bad, I'm sorry, I'm drunk. That's why I get drunk. So when people give me shit because I misspeak, be like, I'm drunk. What do you want, bro? What do you want? And on other things too. I might be a druggie. But I am what I am. And I am the one who conquered gravity. Drugs be damned and all. Can't change what I've done. So, okay, if it's the same distance, the redshift is the same distance as the wavelength itself, then we're going half the speed of light. Okay, so let's kick it up. We know that once we reach the speed of light, or very close to it, let's say 95% of the speed of light, that all chemistry is essentially going to fail, and that these galaxies are going to become desolate death cemeteries as far as life is concerned, and any normal semblance of physics as we know them. Okay, so that's where we're saying the edge of the known universe is going to be, is at that point where the displacement of gravitational field pushing and dark energy is pushing all the galaxies away so fast and so far away from us that at the edge, the outer rim, they're going so fast that they're basically disintegrating. We're going to say that is the end of the known universe. Is really no, there's still other. It still goes further. But for our purposes, to satisfy our monkey mind, to end the infinity paradox, that is the point at which we are going to establish. Okay? So, let's keep going. Let's push this further. Let's say it is 2. So 2 divided by 3, because 2 plus 1. Because remember, 1 is always our baseline angstrom. Now we're at 66% the speed of light. Okay? So technically, that would be a redshift of 2. I want to say. So at a redshift of 2, according to my math, we're already going 66% the speed of light, which is pretty damn fast. Okay? This is not slow. Let's do a redshift of 3. Okay? Let's keep pushing this further. Let's go a little higher. Let's go 5. Okay? 5 divided by 5 plus 1, which is 6. And we are going to get 0.83. Okay? Interesting. And I just realized you cannot see what I am going on about. Okay. Don't worry. I do stuff. I fix stuff. Online calculator. I'm going to make it. I want you to see this because this is important. Okay? We're going to go away from the calculator. I'm sorry I failed you. I suck. I'm sorry. I'm a loser. I know I am. Okay, so once again, let's start at the beginning real quick. We got a redshift of, let's say, 1. And that means we're going to divide 1 plus the baseline of 1, which is 2, gives us 50. 50% the speed of light, okay? 0.5. 50% the speed of light, okay? Now, is that CE? I guess it is. Okay. So now let's go up. Let's try 5. 5 divided by redshift of 5 means 5 times, or 5 units, And we got 1 unit is what it should be. So 1 plus 5 is 6, according to my math, right? Remember, that's my math right here. That's what we're doing, my math, okay? We're going to equal 0.83%, what I said earlier, you couldn't see, I apologize. 0.83%, the speed of light we're already at with a redshift of 5, okay? And we see redshifts of 5 all the time, but they're still not going the speed of light. So let's push this further, okay? Let's say we do a redshift of 10, okay? We got a redshift of 10. It's being shifted 10 times of what the actual unit is. So the actual unit is still 1, as always. We're keeping it simple so our monkey mind can comprehend this simply, what's going on. Okay, divide 10 plus 1 is 11. So 10 divided by 11. Okay, we're at 90.9% of the speed of light now at a redshift of 10. Remember, we cannot go the speed of light. And I would argue to say that once we get past 95% the speed of light, things start getting really, really bad. Okay? All right, let's push this further. Let's go 15. This would be a galaxy, according to my math, that has a redshift of 15. Okay? One higher than what we know of exists. And it most definitely is out there. It most definitely is out there. Okay? So divide 15 by 1 plus 1 is 16. Okay? Now, we're at 93.7, 94%. Remember I said about 95% is probably where things are going to start getting messed up. Okay? Now, remember, a lot of these galaxies that they are showing, okay? They say they are, I'm trying to do this, primitive. Like,
Oh, we're looking back into time. These galaxies are primitive. Blah, 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 blah.
okay, that's true to a certain degree, but keep in mind, the universe is very, very old, okay? I think our current theory of the Big Bang says it's like 13 billion years old or something like that, okay? The Big Bang is bullshit. It doesn't exist. It's completely incompatible with my theory of gravity. So I created a universal origin story that I call the gradual universe. And it's basically based upon very heavily on quantum mechanics, okay? Very heavily on quantum mechanical principles that we know and love, and on how matter is generated from the quantum foam. And from this, essentially, I say that hydrogen or matter would just be spontaneously created in all corners of the galaxy at all times simultaneously. But once you have matter, matter begats more matter. It makes matter faster once you have matter because more interactions are going on there, energy to draw from to make matter. So basically, if I'm correct, we have a universe where hydrogen gas is everywhere, even in the deepest, darkest voids of space. But where matter already is, you're going to have more matter being created at a faster rate. Okay? And this is pretty much, to my understanding, what we see when we look at for hydrogen 21 emissions and all this stuff, you know, and map out the cosmic webbing and all this stuff. This is pretty much exactly in line with my predictions of the gradual universe on how everything should be. If it's the Big Bang Theory, you shouldn't have, dude, if all the matter in the universe was made like that in a single place and it exploded, you should not have hydrogen gas just sitting still with zero velocity in the voids of deep space. But it's there. We measure it. It's there. But according to the Big Bang, it shouldn't be there. Nobody wants to think about this stuff. People don't use their head. They just believe into whatever stuff that the tribe says is the current state of affairs. And it's not right. So, just so you know, according to my theory, that is basically what you'd expect to see of the gradual universe. And I did a big video on this. You can look it up in my YouTube channel and see what I'm talking about when I say gradual universe and the origin of the universe, the Big Bang alternative. Oldest galaxy. Okay. So we're going to try. Now, as these are pictures of like some of the oldest galaxies, and they say that they're very primitive. They're just like, globular galaxies, but they are still galaxies. They have a super galactic black hole and stuff. They say this is because it's such a primitive that the universe was barely alive, but yet we don't know how a galaxy can form in just 100 or 200,000 years. Just doesn't make any sense to us. And as James Webb goes on, it's going to keep finding more and more redshifted stuff. This is not going to get any better for the Big Bang Theory, dude. It's a dead theory, bro. It's done. It's done. They just don't know it yet, but it's dead. The gradual universe theory is the theory that explains the origin story of our universe, hands down. All the data we collect prove it. Watch my video, you understand what I'm talking about. But I say that these universes don't look so primitive because they were just formed. I mean, maybe they could have been, but simply because they're going so fast that chemistry itself is starting to fail. Like they're traveling literally 90 plus 95% plus the speed of light. And remember, according to my theory of gravity, you're going to start having some serious problems when you're going this fast, okay? All chemistry is going to fail. Your universe is not going to be able to develop chemically very well. It's going to start disintegrating. It's going to be very, very bad when it starts going this fast, okay? So just remember, this is what I say. Now, sorry I got sidetracked. I do this all the time. Green image. Okay, let's go back. Let's calculate the size of the universe. Okay, remember, once we get to a very high number, like let's say 98%, we're pretty much going to say that's about the end of the universe right there. Okay, so we got a redshift. 15. We're at 94% the speed of light. Let's try 20. What have we got with 20? A redshift of 20. 20. Divide it by 20 plus 1, 21. 95. Bam! So at a redshift of 20, we're at 95%, right where I say things are going to start getting crazy. Okay? It's still going to be matter there. It's still going to be doing things, but it is not going to look like normal galaxy. It's not going to behave in a normal manner. It's going to start having all sorts of crazy attributes because it's going so fast that chemistry itself cannot keep up. Ergo, we already got rid of it. It is what it is. So let's push this a little further. Okay, we're at a redshift of 20. Okay, already. And we're still not even at the speed of light. We're still 5% from the speed of light. Let's do a redshift of 30. 30 divided by 31. 96% of the speed of You see how slow it's going now? This is getting to be scary if you think about these numbers. Okay, let's try a redshift of 50. 50 divided by 51. 98% of the speed of light. You know what? Let's just go, once we get 99%, let's say 70 divided by 70. 98. So, you know what? I'm going to call it right there. That's where I think about the edge of the universe pretty much is going to be. It's going to go further, don't get me wrong, but at that point, what we see, we're not going to recognize anymore as matter. It's going to have completely different attributes at this point. So I would say a redshift of 50, just out of curiosity, that's 100. 99% exactly. 99%. Let's give ourselves some wiggle room. Let's say 100, okay? So let's say that the redshift of 100 is the farthest object we're going to ever be able to see. Because anything beyond that, all the galaxies are going to be disintegrating into nothingness, okay? Straight up. So 99% the speed of light is what they're going to be traveling if they have a redshift. But keep in mind, as we measure redshift, the galaxy, let's say this is our galaxy. And let's say our galaxy is over here. It's not just this galaxy receding from us. We are also receding from it. So if we have a redshift of that fast, it might not actually be that we're sitting still and that galaxy is traveling that fast. It might be that we're both traveling insanely fast, which means now the speed can, now the distance can get even much further. And then I'm not even calculating the 20% rule that the universe is that much larger than what it was than when we see the light. So keep in mind, this is 100% a lowball estimate of the universe's size, but we have to start somewhere. We have to pit out a number, and I say it is going to be a redshift of 100. Now, if we come to our handy dandy thing, it doesn't even come close to 100, man. We can only guess. But at the rate that this is saying, if it's a redshift of 10, and they're saying it's this far away, which keep in mind, they're also saying that because of the Hubble constant. So that, in actuality, might not even be remotely accurate because we know the Hubble is bullshit. It's just purely speed. Oh my god, this is getting so complicated. So much more complicated than I anticipated. It's such a simple thing. This formula you look at and you're like, yeah, how can it be? Okay. Well, if we do this, is there redshift velocity? No. There is no way to calculate distance from it unless wasn't there a distance formula? Maybe not. Oh well. Can't say we didn't try. All right. So if I had to guess, which I'm completely guessing right now, this is not it is not verified, but this is kind of like a eyeballing thing, okay? We got 13 billion at a redshift of 10. Okay. Let's say they're right. And that redshift has been shifted 10 times, okay? The way this is going, they're going to say that this is probably because a factor of 10. It's gone up. Let's see here, from 4 to 10, it's gone up 1. So it's probably going to go up 2, I would say, to 15, probably, roughly. So they would say that the furthest objects away are 15 billion light years away, but actually, according to this, they'd be like 100 million light years away, 100 billion light years away, going to this extrapolation curve. Man, this is really hard. But if I had to guess, and I'm guessing right now, I'll come out with a better answer for you later once I find some better things. I am going to say You know what? I'm not going to say. I'm going to look for the actual formula. That's what I'm going to do. I know. You have to sit there and watch me. See, the only thing they have is the Hubble constant, though. That's the only thing they have to calculate it. Which is the Hubble constant's not even constant because it's changing, because the universe is accelerating at different rates depending on how close you are to the center of it versus the... But let's say it's true. Let's say it's true. Okay. See, here's one distance. Sorry, you probably can't see. Distance z times c divided by the Hubble constant. Man, the Hubble constant's not going to work, though. It's just not going to work. Can't do it. Yeah, and I think the Hubble constant, too, is kind of a joke. I don't know if we really went into this, but just so you know how ridiculous the Hubble constant is, here's the official Hubble constant numbers. 67. Oh no, but it was 68. Oh, 66. Oh, 73. Oh, another year. 75. 69. 67. Oh, yeah. 75. Oh, blah, blah, blah. 63. Oh, we're going back further. Oh, no. 70. Oh, ho, ho, ho. 67. It's all over the place, dude. It's all over the place. Oh, 100. Yeah, they don't know, dude. It's all over the place. Man, let's say they're right, which I think strongly they are not. The furthest galaxy away with a redshift of 14 is 14 billion light years away. Man. Okay. I'm going to tell you right now. I don't know how big the universe is, but I'm going to say it's bigger than 50 billion light years, okay? If the current estimate is 14 billion light years, 22, including expansion that we haven't seen yet, I'm going to say it's a lot larger than that. Magnitudes of orders of magnitude. I'm going to say it's at least 50 billion light years. Potentially as high as up to 100 billion light years. I mean, it's huge, but there is going to be a defined edge. And so now you might be asking, okay, so there's an edge to the universe. What does it look like? What is this? You know, you told me, you showed me your math, you calculated roughly, guesstimation, how large it's going to be, at least 50 billion light years, which is huge. Keep in mind, this is how far we say the current size of the universe is, 13.1 billion. Well, actually, further than that now, probably like 13.5 billion. But, you know, they guesstimate, oh, well, it's actually like 36 billion, blah, blah, blah. But I'm going to say it's so much larger, dude. We're talking, according to numbers I'm getting, I'm going to say at least 50, between 50 and 100 billion light years. That's what I'm going to say. 50 to 100 billion. I know it's a huge wiggle room, but, bro, there are so many calculations that we have to make that I can't even find right now, the math, because everything is all based around the Hubble constant, which, as I've shown you, is completely off the chain, dude. It's off the wall. It's off the reservation. It's all over the place. They can't even, everywhere they look is slightly different because there is no constant. It's not a constant. It's just simply the universe expanding, and it's expanding from dark energy, but I calculate why that is and how that is and what it is. And yeah, it's just basically black holes playing with each other is all it is, essentially. Okay? So that's the size of the universe, 50 to 100 billion light years that I'm going to commit myself to saying right now at this point in time, subject to change later, of course. But as of right now, that's our starting point. At least 50, no more than 100 billion light years. Huge. Massively huge, but not infinite, but massively huge. But not infinite, but massively huge compared to what our monkey brain can comprehend. So much larger than what we see right now at the James Webb Telescope. So much larger. And now you might be asking, well, what does the universe look like? What shape is it? You're not going to believe me, dude. I know you're not, but it's true. Well, I don't know if it's true. I'm guessing. I believe, I don't have any evidence of this, but I believe from how my gradual universe theory works, where matter is created at all times, in all places, but matter begets more matter. So the more matter you have, the more matter that's generated through quantum mechanic attributes and stuff like this. And according to me, when I run the simulations, when I get stoned out of my mind and run the simulations in my head, what I get of what the universe looks like, the shape of the universe, is a slug. I know. I know. You're like, huh? Yeah. Yeah. Space slug. Okay? Space slug. That's what I call it. And think about this. Okay, let's pretend that this is the universe, okay? This is where all the matter mostly is. And then as you get further away from this slug shape of the core of the universe, where the matter is begetting the most of the matter, you're going to still have more matter coming out. But it's going to taper off until you hit to the point where it's just kind of hydrogen gas. It's not really dense enough to interact with itself yet. And you're going to have a layer of, like I said, these outer galaxies that are traveling so close to the speed of light or at the speed of light to where they actually are disintegrating themselves and destroying themselves from all the dark energy pressure created on them from all your galaxies and your cosmic slug. Cosmic slug. I like that name. Cosmic slug. And you might be asking, well, why not a perfect sphere? Dude, do you know how hard it is to make a perfect sphere? Like, have you ever tried to, like, just and make a perfect sphere? It was literally, like, considered one of the tests of ultimate, skill. Like, I think it was Leonardo da Vinci or someone. They said, prove to me that you're the greatest artist in the world. And Leonardo da Vinci said, all right. And he made a perfect sphere. Perfect sphere by visual counts. And they're like, hot damn, that's actually impressive. Making a perfect sphere is not easy. It requires a lot of work. And in case if you haven't realized, the universe and physics are really, really lazy. They don't like to do work. Okay? They don't like it. So, everything's always in equilibrium, or it'd be called the universe's lazy state, going for the easiest option. And I believe that the easiest option for the universe to create is going to be a blob. But not any blob, an elliptical blob. Elliptical blob. Shaped like a slug. And I believe firmly that in 1,000 years from now, when we develop telescopes that are powerful enough that we can actually image the universe itself and determine where we are at on this cosmic slug. If we're in it in the center, if we're out on the skin, if we're out in the outskirts, wherever we're at, that they're going to be able to figure this out, and they're going to start seeing the image of the universe and the cosmic webs and how it all relates, and it's going to ultimately, at the end of the day, it's going to make a giant cosmic slug. This is what I believe. And I have no evidence to back this up other than that the universe is lazy equilibrium. But I'm putting it out there right now. That's what I believe the shape of the universe is. And this makes trying to define how large the universe really hard, because I want you to think about this. Let's say we're right here, okay? Boop, 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 boop. How big is the universe? Well, it depends what direction you're looking. If we're looking this direction, it's pretty damn big. It could be hundreds of billions of light years away. If we're looking this direction, it might not be that far at all. It might only be 50 billion light years away. You know what I mean? It all depends on where you're at in the shape of the universe is also going to depend how large the universe is. In what direction. I mean, ultimately, the universe is the size of the universe, but what I'm trying to say is your orientation in the universe changes that. Okay? And we have not even a fraction of enough data yet to determine our orientation in the universe. We're just finally starting to get a picture of what the universe looks like around us, much less everywhere. Okay? And like I said, according to my math and my guesstimation, I would say the universe is probably 50 to 100 light years. Never mind, not light years. 50 to 100 billion light years in size. So take from that what you will. I know I fumbled the ball on this this lecture. I suck. I'm sorry. I'm drunk. I'm a loser. You're a good person if you made it this far, man or woman. You have my respect. And that's pretty much it. I'm going to end it right now because my mind is like, I'm so scrambled right now from going all over this stuff and trying to, I can't even. I love you. I'll talk to you later. You have a good day. Adios.
Like, subscribe, submit.